All right. Every time I go to a French conference, people tell me, you should be prepared to answer one question. Where is Brian? So I know the question in advance. Brian is in the kitchen. Have you ever had this feeling of accomplishment, achievement, that you have to do a task and you have done it and you did it actually well? You feel so proud of yourself. For example, last Friday, I've been working for a couple of days on writing some tests, and on a Friday, I managed to achieve 100% code coverage. It's a magical moment of our life, right? In our lives, when we see the screen showing 100% code coverage, yes, we did it. And you feel so proud of yourself. You did something good. You are so sure that you have done your job correctly. And you feel that you can go on weekend safely. Unfortunately, you arrive on Monday, and you see that your mailbox is flooded with many of messages, bug reports, and then you ask yourself, what I have missed? What happened between Friday, where I achieved 100% code coverage, and Monday? There's something went wrong. Historically speaking, in the past, long time ago, when we want to make sure our program is running correctly, doing what it's supposed to do, we're actually running it manually several times, making sure if there are bugs, trying to fix it. However, this approach is not going to work when number of lines of code are increasing, number of classes, packages, and so on. With the growth of all those technologies, features we are implementing in our program, this approach is not efficient anymore. Afterwards, there is those test frameworks appear to help us trying to find bugs much faster and efficient way. For example, the PiTest or the unit test for Python, GUnit for Java, and so on for the other programming languages. But still the question remains. And actually, those tools, they provide us with what we call code coverage or test coverage, which is a percentage telling us how many lines of our code has been executed by our test suite. However, the question remains is, actually, when I get 100% code coverage, does that necessarily mean that I'm 100% sure my code has been really and efficiently tested? I'm sure what I have wrote guarantees that I'm covering all the edge cases in my code? Unfortunately, the answer not necessarily. And we're going to see that why. Well, hi, everyone. My name is Maha. I'm an engineering manager at Elastic. I'm leading a team where we are providing guidance and framework to the other product team at Elastic to help them and empower them to produce reusable artifacts. I have a PhD in optimizing performance of multi-tier distributed systems deployed in private cloud. I'm supposed to give this talk with my co-speaker, Olivier. He's an advocate, a developer advocate at AWS, but unfortunately, he couldn't make it for today. So it's going to be me, and I'm going to talk to you today about mutation testing, how we're going to implement it, how we're going to benefit out of it. So let's start by answering the first question. What's the mutation testing? Well, I'm going to tell you that mutation testing, it's a technique that helps us to evaluate the efficiency and the effectiveness of our test suite. By giving us a score, what we call it mutation score, we're going to talk about it in more details in the coming slides. Historically speaking, the first appearance of this concept was actually by a student named Richard Leplus in 1971. However, the first implementation appears as a PhD work of a student at Yale University in the 80s. Why do we care about this concept? So in a nutshell, I'm going to tell you that mutation test is testing the test. So you might be surprised, like you are asking me, I'm working my hard to write test, and now you are asking me to write the test to test the test. This is a bit crazy, right? But let's break down all these concepts to small chunks to better understand how we're going to benefit out of it. So why do we need the mutation testing? Well, there are several reasons. The first one is, as I mentioned, 100% code coverage doesn't really necessarily means that we are sure 100% that our code does what it's supposed to do, and our test is so efficient, and we are able to detect all the edge cases. So it will help us to evaluate the efficiency of our test suite. Of course, it will help us to improve our test suite and its capacity to detect bugs and edge cases. And last but not least, it will help us to pinpoint any regression in our test suite. How we are gonna use this mutation testing and how we implement it? So the idea behind mutation testing, what we need to do, we need to create a modified copy of our original code, where we introduce one modification, small modification at a time. So in general, mutation testing is you test the efficiency or the capacity of your test suite by introducing small faults systematically seeded into your program. And remember, there is only one fault, one change at a time. Okay? There is a lot of information here. Those modifications, or each modified copy of our code, we call it a mutant. So let's start by the mutant. What's a mutant? A mutant, it's a modified copy of our original code, where we have only one modification. And then we run the relevant test against that modified copy of our code. And the goal is to have the test failing. You might be surprised. What does that mean? If the test fails against this modification, that means that the test was able to detect this modification that I introduced in the code, which is good. So I kill the mutant. But if the test passes, this is not good, the mutant will survive, meaning that my test is weak, wasn't able to detect this modification I introduced in the code. Let's take an example. So first of all, how many of you develop some Python? Okay, that's great. How many of you develop in Java? Wow, wonderful. I have two demos, one in Python, one in Java, so everybody will be satisfied at the end. Okay, let's start by looking at this simple example in Python. So here's a simple method. I'm computing a square root of a number. So my input is a number, and I check if this number is smaller than 0, I raise an error. Otherwise, I return the square root, simple. And I write the test, the unit test for this method. So simply put, I have only a assert statement where I say, OK, the square root for 49 is 7. So if I run this test, it will pass. Everything is fine. OK. Now we want to create a mutant of this code. We want to make sure if this test I just introduced is enough or not. So a way to create a mutant, as I said, I create a new copy of my original code by introducing only one modification. So here what I'm going to do, actually, I'm going to change this operator from if the number is smaller than 0 to smaller or equal to 0. So I did small modification. And then, so this is a mutant. The new copy is a mutant. And then I will rerun the test again against that modified copy. What will happen? Actually, the code will pass and the test will pass. Why is that? Because the modification I introduced doesn't impact what I have wrote in the test, which means that the mutant survive, meaning that my unit test wasn't sufficient enough to detect this modification I just introduced. So the goal is to kill that mutant. And how I'm going to kill that? By improving my unit test. That's what we said, the goal from the mutation testing. So I'm going to improve my unit test by adding another statement, assert statement, where I'm saying, actually, the square root for 0 is 0. And then if I run the test, so the test will fail, but the mutant will be killed. And this is the goal. So the mutant got killed, meaning that my test was able to detect this modification I introduced. All right. So I showed you a simple example where I made only one modification to generate or to create a mutant. That modification was arithmetic modification from smaller to smaller or equal. However, there are different types, hundreds of types. I'm going to narrow it down to 3 main types. The first one is the value mutation, where you can change a value of a parameter or a variable you have. It can be number, mutant, or it can be string mutant. Okay. There is another type which is involved in this category, the decision. So meaning that you change a condition, that you switch the if-else block, you change and to or to and so on. And there's the other kind where actually it's a statement mutation, where you remove complete block from your code, or you inject a new line of code in your program. All right. So let's have more example on those different kinds of way to create mutants. So the arithmetic operator, as I just explained to you, and for example, I can change the plus to minus, I can change the divide to multiplication, and so on. So those arithmetic ones. There are mutants can be created if you have arrays. You change the declaration of the array to make it empty. There are mutants can be created for assignment expressions. Other type for block statements. So for example, I have this function where there is a log, okay? The mutant, equivalent to mutant, can be removing completely the log statement. So I completely changed the original code by introducing one modification. What I want to say, actually, there are plenty of kinds. Here is the Boolean. You change it true to false, false to true, vice versa. It happens. Those types, they might vary, depends on the programming language. There are some of them, they are existing in some programming language, they don't exist in the other. So that's really depends on the specificity of the programming languages. But it's worth to say that there are plenty of them. Conditional, quality operators, logical, strings, and so on. So the list really can get longer. I'm not going to go deeply through all those types, but you can discover them, and those, again, depends on the programming language. I think now you might tell yourself, OK, you are introducing all those, and you are asking me to write thousands of copies of my code, and by changing one, doing only one change at a time. So this is really overwhelming. So don't panic. You don't have to do that, because there are plenty of tools that can help us to do it automatically. The other good news about this part is those tools also, they provide what we call the mutation score. The mutation score simply computed the number of mutants you killed divided by the total number you generate. And of course, the higher this score is, the better my unit test, my test suite is. So I can be more sure that my test suite is more efficient and it's able to detect if there are edge cases or bugs hidden in my code. I think we got the general idea about the mutation testing and what's the goal behind it. Let's go into a demo. I think everybody will love the demo, right? You agree with me, guys? OK. So the first demo, it's a Python demo. It's the font size is good for everyone, or should I increase it? It's good? People in the back, you see well? All right. OK, so here is my Python example, where I simply have the calculator to make it simple to understand and to follow. I implemented different functionalities, the basic ones for the calculator: add, subtract, multiply, divide, square root, and power. I also implemented simple unit test for that. So for each function, I have some assert statement where I'm testing all those functionalities. So the first thing I'm going to do, I'm going to run my test, okay, to make sure it passed. So it passed. I have 6 tests, and they are passing. The second thing I'm going to do is let's run the code coverage to get how much code coverage we have for this. And as you can see, we have 100% code coverage. Wow, great. OK, so at this moment, we feel everything is going well. I have code coverage 100%. Perfect. Let me, before running the other, the mutation test tool, for Python, there are different tools. The first one is the MutePi. The installation pretty straightforward. So using pipe, you can install it directly. And what you need to pass 2 main parameters is the target, where is your source code, where you need to mutate that source code, and the unit test. And there are other parameters to show the result, to show all the mutants has been created, and to generate report. That's great. And this report can be in JSON, XML, I think, and HTML. So me, I'm going to go back to my code. I'm going to run the mutation for the MutePi. There is one note here. If you notice that actually in Mac, this MutePi doesn't work, so I had to run it inside the Docker. It's still the command is the same exactly. I'm passing here the MutePi, the target, the unit test, and the other parameters to generate reports. So I'm going to run that. And as you can see here, that what I got actually mutation score only 64%. And if we go back from the beginning, he will tell me all kinds of mutants have been generated out of this source code for this calculator class, and what he has introduced as a change. So for example, he has changed the multiplication to this operator, and the mutant can get killed by my test, which is good. Change the multiplication by divide, got killed. Minus by plus, got killed. But there are things they didn't get killed, they survived. Let's look at some of them. Actually, there is one here, or there is another one here. When he is changing, actually, the not only operator is changing the value itself. So there are mutants hasn't been killed by my test. So if I want to kill this one, the square root, because the one we took, this means that I need to change something in my test. So if I go back to my test, and what I do for the square root, for example, if I want to make sure that I will kill the mutant for that, I can add another statement for the 0. Sorry. Of course, the test is fine. And let's run the mutant again. And we should see that the percentage, the score increased, has been increased. And if I go back here, actually, has been killed. He is telling me it has been killed, this mutant, where I change the smaller to smaller or equals 0. So in this way, I managed to kill this mutant. And of course, you have to do it for the rest to be able to reach 100% or higher score. OK? So I'm going to show you the HTML report for that. So as you can see here, it will show me in a nice way, readable way, the source I started from, what's the test I target to run against those mutants that I have generated, the score, the time it took, and here it will list all kinds of mutant has been generated with the result, if some of them get killed or some of them get survived. Of course, the type of the change you created, changing a value, changing an operator, arithmetic, logic, and so on. So you can even go into more details and to see what happened and to read more about those mutants. All right. So this is the first tool, was a MutePi. However, it has been like since 2019, I think, the Rust release, so the community there is not active. There are other tools for Pythons for those who love Python. So there is a mute. I tested it as well. The installation is straightforward. You can customize it actually to say what kind of mutant you want to generate, what type. I noticed that number of mutants here are the generated ones are less. So for example, for the same exact example, there were only 10, while for the MutePi, there were 14. But I guess this number can be customized. There is another one, which is actually the community there. It's pretty active. The last version was, I guess, in last February this year. Also, the installation using pipe, it's straightforward. A Mutation Test. And this one is really working for the PiTest. When you have PiTest, it works well for that. The MutePi works for the unit test. All right. So we are done for the Java people. Let's move to the, for Python people, sorry. Now it's the Java people turn. So for Java, there is very well-known, widely used mutation test tool called the PiTest. PiTest is, you can really install it straightforward. It works if you want to, you are a big fan of Maven or Gradle or Ant or by command line. So me, for this demo, actually, I choose to use it for Maven. And how you're going to integrate it or make it work for Maven, the installation is really straightforward. So basically, you go to your pom.xml, and inside this build plugins, tags you need to insert. The group ID, this is a plugin exactly, where you are specifying the group ID, the PiTest, and the artifact ID for the PiTest Maven, and of course, the version you would like. Okay? And there are two goals you need to run. The first one is the mutation coverage goal, and there is another one, SCM, when you have your code linked with the source control system, and where you can filter files that you need to generate mutation for those files. Basically, they will be when you add new files or you modify some files. So I'm going to focus on the main first goal, which is the mutation coverage. So let me go to my IDE, which doesn't appear, a bit surprised. Okay. So this is, I don't need it anymore. And I am in this one. Okay, let me just try to exit. Seems it's stuck somewhere. It's the curse of demo always. All right. Yes, please. Okay. It's clear also the font size for you? People in the back? Good? It's small? Okay, let me try to increase it. Appearance, and okay, like this probably. Better. Okay, so what I was saying, the installation for the PiTest is really straightforward. So you go to your pom.xml, and here inside build the plugins, you put the plugin referring to the PiTest. Okay, in Maven, sorry. What I like about it, actually, it's very customizable. Meaning, you see there is the configuration section where I can say what the target classes I would like, because sometimes you don't want to actually to mutate to run this mutation test against all the classes. So you can specify what package, what the classes, what those tests you are targeting also to run against those mutated copies of your original program. There are other things actually you can specify, as you can see inside this tag, muters. You can decide what type you want to generate. So for example, I don't want to generate all kinds. I want just to be specific to arithmetic operator. Just I want to test those. Or I want to be specific to constructors. I want to check just if I have enough tests for those or not. So you can specify that. That's really cool. You can also specify what in this tag avoid calls. So when you have like calls to logging, so probably you don't care about those things. If there is code calling logging services, you don't care about those. You don't want to generate. So this is meaningless for you. So you can also exclude those from being mutated or generating mutation for those kind of methods or cases. All right. And again, I'm not nothing here magic. It's you have the same exact example. I kept it simple, and I have the test for it, which when I run the test unit, it will pass. However, I have only code coverage 50%. Why I did that? I did that on purpose, actually, to tell you if you want to run mutation test, has nothing to do with having 100% code coverage. There are two different things. So you can run mutation tests whatever the code coverage you have. Okay, if it's better, it will help you to probably to analyze faster, but you can run it even with code coverage only 50%, it's fine, or whatever. Okay, and I'm gonna run my goal, which is this one, as we said, it's the mutation coverage with Maven. And here is telling me my mutation score only 70% because there were 10 mutants have been created. Only 7 of them got killed. There are 3 still alive. And if I go scroll up, I will see that those kinds of mutants were generated from 3 different types. One of them void method call, one of them math, and the other one primitive return metadata. Doesn't give me more details apart from this, but still not bad. There is also XML reporter will be generated. Actually, I can show it to you. It's not as fancy as the other one, but just to say, it's showing like you have the code coverage 50% and the mutation coverage is only 70%. So it's not as fancy as the Python one, but it helps. Better than nothing, right? All right. So this is for the Java code. And so we've seen 2 demos, one in Python, one in Java. And we've seen we can apply mutation test regardless the percentage of the code coverage we have or the test coverage we have. Again, I want to recap and insist on the fact the relation between code coverage and mutation score. Code coverage is nice metric to have. It's good. The higher you get, it still is good, right? And again, having 100% code coverage, seeing that in our screen, really, it's a magical moment in our lives, and we are super happy about it. But still remember, it's not enough to make us 100% sure that our test suite is sufficient and it's effective to detect there are edge cases or bugs in our code or not. And that's why we need another tool or another metric to help us to evaluate the effectiveness of our test suite. Why do we care about this? Because the test suite is really our source of a truth to tell if our code does what's supposed to do and if it's really there are no hidden or uncovered bugs or edge cases. That's why we introduce mutation testing, testing the test. And the mutation score will help us to tell how effective our test suite is. However, some of you might think, OK, if code coverage is not enough, 100% it's not enough, I can try probably always to keep getting 100% of mutation score. Well, this is sometimes can be difficult, and there are reasons. So you don't need to really work super hard, just your target to get 100% also of mutation score. Why is that? Well, actually, because there are other kinds of mutants, what we call them equivalent mutants. What are those equivalent mutants? Those actually change copy in the code, but this change doesn't really change the logic of our original code. Meaning, let's have a look at this example. I have this example in Python where I want to get a web page by passing a URL. So me, as an optimization, what I say, OK, let's use dictionary in Python, where the first time I get this web page, I will save it in a dictionary. The key is the URL, and the value is the web page. So second time I get the same URL, I don't need to go to the internet to fetch this web page. So optimization, all right? And then a mutant can be created for this kind by, by removing one block. I told you that one kind to create a mutant, you can remove completely one block of your code, disappear. So if a mutant created by removing this condition where I check if the URL already in the dictionary or not, actually the test will pass, will not be impacted at all. So the mutant will not be killed. And those, in this case, you will not reach the 100%. And those cases, we call them equivalent to mutants, and they're not going to be killed. So we can ignore them. Unfortunately, there is nothing perfect in life. So even with all those tools, there are limitations. So the limitation of mutation testing is that it can be time-consuming. What I showed you, it was simple example calculator, but can you imagine it with big code, bigger project, how it's going to look like? So it's overwhelming to the developers to do so. And that's why we need to use those tools to be able really to help us to automate all the process. Here, actually, you might ask yourself a very important question. How can I run still mutation testing at large scale? And there is actually a paper has been published by Google in 2020 where they are using mutation testing. So they are running it in their code base where they have 2 billion lines of code and 150 million tests that are running on daily basis. Can you imagine how many mutants can be created? You don't need to think about it. It's really like blowing the mind, right? So what they did, actually, but still they want to benefit from that. So what they did in this study, it's really great paper to read. They said, OK, here's our approach. What we want to do, we will limit the number of a mutant created by each, depends on the operators that we care about, and that will benefit from really some historical information from the developers. So we can filter out some mutants that we don't care about. We can filter out those equivalent to mutants. As we can, I showed you, those they don't really change the logic of the application. Very important point they propose, and they are doing it, which is doing mutation incrementally, meaning that I apply the mutation on only the new introduced code, and I limit the number of mutants created per each line of code, per each PR, per request. In this way, you are able incrementally to improve your test suite. Last but not least, as I said, you need always to know the source code, the original program, because you need to modify it. So mutation test cannot be applicable on a white box. So it's always in black box, always white box, because you need to know the original program to be able to modify it. As takeaway, again, this is my message. 100% code coverage doesn't mean that everything is fine. It's good to have it, but it's not enough, and that's why we need another metrics, which is the mutation score. What we care about here, it's the quality rather than the quantity. We all know, if you are developers, and the majority yes, we know that we can reach higher number or higher score in code coverage by writing bad tests. We are able to do so. So this is not enough. We care about the quality, not the quantity. And of course, this can be overwhelming, so we need automation thanks to those existing tools. Last but not least is that sometimes also mutation score, getting 100% mutation score can be difficult because those equivalent to mutants. Well, for the other programming languages, no worries. There is a Striker for those who develop in JavaScript. There is for C++, PHP, Ruby, Rust, Swift. So for different programming languages, there are those tools to help you to implement and integrate the mutation testing. Well, I guess I reached the end of my talk. I really enjoyed giving this talk. I hope that you learned something with me for Python, Java, or any other programming languages. The concept is the same, regardless the programming language. I hope you will go back to your team, tell them about it, and try to run it, and probably share with us the mutation score you have today. Thank you so much, everyone.